Yeah, so before we start today's class, I think it's been some time since we met. So do you can you let me know what we discussed in the last class? Do you remember? Okay, so again, specifically, we were discussing about advanced ILP, advanced instruction level parallelism. Okay, so one of the techniques of implementing instruction level parallelism is pipelining, which we have already studied. And the second way of increasing the instruction level parallelism is having multiple issue processors. Okay, multiple issue processors basically means that you will be able to fetch two instructions at a time, decode two instructions at a time, and so on. Okay, so there are mainly two types of uh, multiple issue processors. So can you tell me what are those two types? And last time, what did we discuss? Which type did we discuss? So there are two types of multiple issue processors. If you want to categorize it broadly, there will be two types of multiple issue processors. What are those? One is basically static, the other one is dynamic. Okay, so you have multiple issue processor static. So static multiple issue, majority of the work is done at the compiler level. So it's compiler which groups the instructions into something called as issue packets, and then the compiler basically detects the hazards and tries to avoid them. So majority of the work is basically done at the compiler level. And then you have your dynamic multiple issue. So dynamic multiple issue where the CPU chooses instructions that are to be executed, and the compiler might still help in reordering instructions so as to reduce the effort to be done at the processor level. But the work done at compiler is minimum. So majority of the work will be done at the CPU level. The CPU itself will resolve the hazards and decide what instructions to execute and so on. So we have discussed about this. Okay, so the static multiple issue processor we have discussed. The example that we took had a two issue size. The issue size was two, where two instructions were fetched at a time, they were executed, and so on. Okay, so that was the example of static multiple issue. Now, coming to the dynamic multiple issues, an example for that we'll be discussing in today's class. Okay. So dynamic multiple issue processors are also called as superscalar processors. Okay, so the CPU decides here whether to issue zero instructions or one instruction or two instructions in each cycle. Again, while issuing, it will make sure that the structural and data hazards are avoided. Okay, so structural hazards are avoided by making sure that enough functional units are available. And it avoids the need for compiler scheduling, though the compiler scheduling might still help to some extent in the execution, but majority of the work will be done by the CPU. Okay, it decides whether to issue zero instructions or whether to issue one instruction, two instructions in each of the clock cycle. Okay, so this is basically what we'll be discussing briefly. Again, there are many algorithms which are used in the implementation of superscalar processors, which will not go into. We'll just look at a brief overview of how the processor is organized and how it will work. Okay. So, and here the dynamic scheduling basically, it's also called as dynamic scheduling. It will allow the CPU to execute instructions out of order. Okay. Normally, when a sequence of instruction is given, let's say you have add, you have sub, and then you have, let's say, PEQ or some other instruction. So you are supposed to execute in this order on. Okay. If there are multiple instructions which are independent, okay, which are independent, then you don't have to execute in this order if a particular functional unit is free at that time. For example, let's say you have add and you have multiplication. Okay, so this is like, let's say, T naught, comma T1, comma T2. This is S naught, comma S1, comma S2. And this is some other instruction which is add, uh, maybe some data dependent instruction, we can say. Okay, or it could be some other instructions. In this case, so you don't have to always follow this order. While this instruction, let's say there is another instruction before this, which is actually getting the value of T1. Let's say, for example, let's say load T1, comma 0, T0. Okay. So this is some instruction. So here you can't execute this add instruction unless T1 is loaded. Only once T1 is loaded, you'll be able to execute this instruction. So, but this is an independent instruction, okay, not dependent on this or this. So if at all you're trying to execute this instruction, you have to wait till T1 is ready. But at the same time, if there is a multiplication unit available, you can execute this before the add instruction. Okay, so that is what we call it as out of order execution. Okay, so it will basically tries to fill up the empty clock cycle. So here, if it has to wait, it will involve stalls. Stall meaning what? It will not do anything. Instead of not doing anything, why not execute an instruction which might come later, which is not dependent on any of the earlier instructions, and if the corresponding functional unit is free, why not fill the stall with the execution of multiplication, okay, or some other instruction which is independent, okay. So that's the basic idea of out of order execution, okay. But it has to make sure that the writes happen to the register in order, okay, because of some issues, okay. So you have some issues with respect to exceptions, you have some issues with respect to branches. So in those cases, you have to make sure that the writes have to always happen in order, okay. So that is why the execution might happen out of order, but they call it a commit, where you actually write the result into a register. So that will always happen in order. Okay. So that's the feature of superscalar or dynamic multiple issue processors. Okay. Dynamic multiple issue processors involves dynamic scheduling of instructions, where instructions can be executed out of order. But even though the execution can happen out of order, the writing part, the writing to the registers part should happen always in order. Okay. So this is again a similar example that we took. So you have these instructions to be executed. You have load T0, 20, S2, add. Again, you can think of it as simple add instruction. So add is basically sent. So add T1, T0, T2. So here, can you start sub instruction while add is waiting for LW? So here, if you see the T0 value is being used in the next instruction. So this instruction has to wait for execution of this. Whereas when I say sub S4, S4, T3, is this instruction dependent on the results of these two? Can I execute this before the add instruction itself? It's very similar to the example that I gave you. Can I execute the sub instruction before the add instruction? So what should be the what should be available so that I'll be able to execute this before addition? What should be available for me? Available with me. Okay, so normally when we talked about the single cycle pipeline processor in the case of RISC-V, we said that there is always one ALU, right? But if you have only one ALU where you have addition and subtraction operations to be done, so then you can't execute sub before add, or the add also might be in the data path. Right? The inputs might be available at that time. If sub also is trying to use the ALU, it will be a structural result. So in most of the dynamic scheduled processors or this dynamic multiple issue processors, you will have lot of functional units. Okay, large number of functional units will be available. Okay, you will have adders, you will have separate multipliers, you will have multiple adders. Okay, multiple adders meaning you will be able to do multiple addition operations at the same time. Okay, so that's one of the major differences between your normal implementation and the dynamic multiple issue processor. Okay, so you will have multiple functional units. So here, can we start sub while ADO is waiting for a load? Yes, we can. Okay, so that's the basic idea. So typically there will be many stages in the dynamically scheduled processors. So the first unit, they call it as instruction fetch and decode unit. And then you have something called as reservation station. I'll talk about this a little later. And these reservation stations are connected to the function units. You have integer function units, you have two integer function units, you have one floating point function unit, and you have a separate load store unit, which is available in this type of processor. Now coming to the reservation station is nothing but a register. Okay, so you'll have a set of registers here available in these blocks to hold the operands. Okay, so whenever the operands are read from the decode part, the decode basically is reading of registers, right? So once the registers are read, they are not directly used; they are kept in the reservation stations. Okay? So it will be very useful whenever you want to modify a particular register that you are trying to read. Okay, so if you have some case like this, add R1, some register. Okay, I'm not specifically talking about MIPS, so sorry, RISC-V. So this register that I'm using might be in general. Okay, so you have add R1, R2, R3. Okay, let's say I am using one more instruction, which is add R3, S2, S4. Now, can you tell me, are these two instructions dependent? First, are these two instructions dependent? No. So my question of two instructions being independent is, my definition is, I should be able to execute in those two instructions in any order. Now, if this is the actual order, can I execute the same instructions in this order? Add R3, S2, S4, and add R1, R2, R3. Instead of following 1 and 2, let's say this is 1 and 2 instructions. Instead of this, can I execute 2 and 1? Is it possible? No. In that sense, it is, in that case, it is not independent. So what is the dependency here? What is the dependency? Till now, whatever we have been doing is we have been seeing instructions like this, where you have add R1, R2, R3, some registers. Then you have add R4, R1, or some registers, R5. So here there is a dependency. Okay, so we only talked about this dependency. Okay, we call this as data hazard. We tried to resolve it using forwarding unit or all of those things. Okay, but this is only one kind of dependency. So this dependency, we call it as read after write. Okay, meaning what? You're supposed to read R1 register only after you write into R1 register. Okay, so that's why it is called as read after write. Okay, so this dependency is called as read after write. So now can you tell me, are these two instructions dependent? So these two instructions that I talked about earlier, okay, these two instructions, are they dependent? So earlier you said no. So can you tell me now, are they dependent? If they are dependent, how are they dependent? How are they dependent? So this dependency, we call it as RAW dependency, which we have studied as part of our normal RISC-V processor. Now here, what kind of dependency is there? Where is the problem coming? With respect to which register? With respect to R3. So what kind of dependency is this? If I follow a similar naming convention, what kind of dependency is there? So you said that there is a dependency with respect to R3. I cannot execute in this order. I can't execute this instruction first and this instruction, because your R3 will get modified and you will be using a wrong R3 in the next instruction if I execute this first and this second. Okay, I have to maintain this order. So if I have to maintain this order, okay, so what is the problem? So just like you have RAW dependency, so we call it as RAW hazard. Okay, hazard. So here, can you tell me what is this kind of hazard? So here, this kind of hazard, we call it as write after read. Okay, because you are supposed to use R3 first. Let's say R3 initially contained value. Okay, so R3 initially contains some 6. Later on, it is getting changed to 7. So here, when I execute this first instruction, I have to use the value of 6. Later, it can change to 7. So you are supposed to write into the register only after read happens. So in that case, every time you can't wait for this instruction to be executed. So that is where the reservation stations help you. So what happens in the reservation stations is, so they'll first read this R3 value. Okay, they'll first read this R3 value and they'll put it here in the reservation station. So R3 is equal to 6. Now the register unit is free. Okay, the register unit has already sent the value of R3 and they have kept it in a register. They might not be used in the functional unit yet, because the functional unit may not be available, or it might be waiting, or whatever be the reason. So once you have read, once you get the value of 6, now even though this instruction is not executed completely, can I execute the second instruction? Can I execute the second instruction in that case? Yeah, so let me explain again. So what I'm trying to say is, so your RT initially had 6, okay? And in the first instruction, you're supposed to use the value of 6. The next instruction is modifying R3. Okay, so let's say you are trying to put these two executions. So let's say it is the first instruction is executed here. So add R1, R2, R3 is supposed to be executed in this integer unit. And let's say the other instruction add R3, S2, S4 is to be executed in this unit. So in this case, if this unit is not free, or let's say if R2 value is not available, okay, well, normally what happens if R2 value is not available, till R2 value is available, this instruction will stop. And if this instruction is stalled, since the second instruction is dependent on this, this also has to stop. Now that can be avoided with the help of reservation station. How do you avoid it? What you do is you first read the value R3 and put it in a register file. Okay, put it in a reservation station. Reservation station basically consists of a copy. It basically consists of some temporary registers. You can think of that way. Okay, so you put the value of R3 here. Now, once the value of R3 is put here, you don't have to. The second instruction need not wait because R3 value is already stored somewhere. Okay, even though your R3 value changes now, it will not cause a problem because R3 value is put up in the reservation station. That way, you don't. This instruction need not wait till the completion of the first instruction. Okay, so that's the reason. That's where your reservation stations will help you to avoid write after read hazard. So this is basically called as write after read hazard. So this hazard can be avoided with the help of reservation station, where you make a copy of that value, that register value, and put it here. And the next instruction, which is actually writing into the register, can go on executing without any issue. Okay, so that's where your reservation station will help you. Okay, so you have instruction fetch and decode unit, you have reservation stations, you have functional units, and at the end you will have a commit unit where the actual writing happens. Okay? Now let us try to analyze this with an example. So there are a few things you have to understand. So while instruction fetching and while decoding, this happens in the same order as instructions that appear in the program. This is called as in order issue. Now it will preserve the dependencies because your program should not change its behavior. The behavior of the program should still be the same. So that will happen only when you maintain the order correctly. So that is called as in order issue. And then you have reservation stations where you will have the operands. Okay, it will hold the operands. So this will help you in basically avoiding the WAR type of hazards. Okay, right after read hazards. And then you can execute out of order depending on the availability of functional units at that time. Okay, and you can also involve forwarding. You can either forward the value from the output of the execution unit, meaning from the output of functional unit, to either the reservation station. Okay, results sent to waiting reservation stations, or you can also send it to the register file for updating. Similarly, you have a commit unit where the actual writing happens. So once the actual writing is happening, so then also you can send the values. You can supply the operands to the reservation stations that are available. Okay, so this is just a gist of how the processor, the different units that are available in the dynamically scheduled processor. Okay, and here there are reorder buffers that will help you to make sure that the write happens always in order. So let us take an example. So if this is the sequence of instructions that I have to execute, you have load T0, 20 S2, you have add T1, T2, T0, T2, you have sub S4, S4, S3, and you have SLTI set less than immediate, where you are just checking S4 with 20, and if S4 is less than 20, you will set T5 to be equal to 1. So these are some of the instructions that are to be executed. Now, as I said, the issue will always be in order. So you execute, you first fetch this instruction, decode this instruction, next you fetch this, and so on. Okay, so that order will not change. Now, whenever you are trying to execute, so first instruction that will be scheduled is, first it will check whether the functional unit is free or not. So since I am not started with the execution, so functional units are free. So your load instruction will go and start executing here. the operands related to the load operation will be loaded in the reservation station. Now, can you tell me which instruction should I schedule for execution? Can I schedule this instruction for execution? Yes or no? Can I schedule at T1, T0, T2 for execution? No. Why is it? Why can't I schedule that? Because there is a dependency on T0. So load instruction has just started executing. We don't know how many clock cycles it might take. Okay, so let's assume that it is, even if it takes 1 clock cycle, unless the memory is read, you will not be able to get T0 value. Okay, so that it has to wait. So where it waits is it waits in the reservation station. It will not execute. It will be waiting in the reservation station, meaning your T0 slot will be kept empty, saying that it is waiting for some other function unit to produce the result, and the T2 value will get loaded. Okay, T2 value will get loaded, but T0 value will not be loaded. It will be waiting. Okay, it will be waiting in the reservation station. Okay. Now, once it gets goes to the reservation station and it waits there, what about sub instruction? Can I schedule that now? Can I schedule that? Why can't I schedule that? Because there is already one instruction in the integer unit. No, execution is going on. Either load store it is going on or it is waiting here. So how can I execute this sub instruction? How can I schedule this sub instruction? There is another integer unit which is free. There is another functional unit which is free. So what I can do is I can schedule the sub instruction in this functional unit. Okay. So this is how I'll be able to schedule. Now, what about this? Can I schedule this instruction SLTI 35, S4, 20? Can I schedule this instruction? No. Why? Why is that? There could be many reasons, right? So here you have no functional unit free. Okay. So what is this hazard? What kind of hazard we can call this? So I'm not able to execute, or I'm not able to execute or schedule this instruction, right? So this is like kind of an hazard. Okay, in every clock cycle, I want to execute new instruction. I want to schedule new instruction, which is not possible here. So how can I categorize this hazard as? In what category can I put it in it? Is it a data hazard? Is it a control hazard? Or is it a structural hazard? It's a structural hazard. Because of the limitations of the hardware, you are not able to schedule this. So we can categorize this as structural hazard. So this has to wait. Okay, so there will be some stalls for this execution. Okay. Now what happens? The sub is not waiting for anything, so the sub can execute before only. So this is like out of order execution. Then your load instructions might complete. Okay, and once your load instruction completes, your T0 value will be ready. So that T0 value will be forwarded. But before the T0 value is forwarded, you have one of the functional unit as free. So what you can do is you can schedule your SLTI now in the second functional unit. Now you can forward the value of T0 because you remember one of the registers T2 register contents was available, whereas T0 was not available, but now load has completed its execution. So T0 value is ready. So that will be forwarded to the resolution station. And then this execution will start. Okay. And the execution will complete. So add instruction will execute next. And then you have SLTI instruction, which will be completing next. Okay, so this is basically saying that I'll be executing out of order. So I started with some order. This was my first instruction, second instruction, third instruction, and fourth. Now when I execute, I'll execute my third instruction first, my first instruction second, and my second instruction third. My fourth instruction is executing in the fourth place only. Okay, so this is basically an idea of out of order execution. Okay. And then when you actually write, you don't write it in this order. You have to maintain the right order. You first write into T0 register, then you write into T1 register, then you write into S4 register, and then you write into T5 register. So this order of writing has to be maintained. So that is achieved. Both add and SLTI execute in parallel. Yes, both add and SLTI will execute in parallel because there are two different functional units available. So this order has to be maintained, this writing order. Now the writing order maintaining will be done by something called as ROB, register reorder buffer, again, which is out of scope of this discussion. But if you want to know, you can just look what register your buffer is. So that's how you'll be able to maintain writing in order. Okay, so in the same order has to be maintained for writing, the same register writing. Okay, so this is just a brief overview of the dynamically scheduled processor or dynamic multiple issue processors. So here you will end up with different kinds of data hazards. Okay, so till now we have only seen read after write kind of hazard, where we have a dependency on T naught, and that is basically used in the T naught value is supposed to be used in the next instruction. So in this case, this instruction cannot execute before this. So this is called as a read after write hazard. So this can be solved with the help of forwarding or stalling. Okay, and you have another hazard, which is basically the example for this. Also, we have the example for this we have not seen. So other hazard is something like this. So you have load T0, 20 S2, and then you have add T0, T2, T1. Now, can I execute this instruction before? Can I execute this add instruction before? Let's say there is another instruction here, which is say add T3, T0, T1. Now, if this was your original execution, can I execute in this order T0, T2, T1? Then you have load T0, 20 S2. And then I'll execute this add T3, T0, T. Will this be correct? Will this be correct execution? No. Oh, why? Why is that? So this is wrong. Can you tell me why is that? So if this is your normal order, the T0 value should come from your result of the add instruction. But if I execute instructions out of order like this, I'm getting a value which is coming from load, which will create a problem. So in this case, we call it as write after write. Okay, so this is a hazard where we say that this instruction cannot be executed before load because the write order has to be maintained. Okay, so this is called as write after write hazard. Normally, this kind of hazard is resolved with the help of the reservation station and register reorder buffer, which is beyond the course. Okay, we'll not discuss that here, but you have to understand that in this case, we can't execute these two instructions out of order. Okay, so that's the main thing that you have to understand here. And another example also we have seen, which was your write after write hazard. Okay, so write after read hazard, where you have something like this. So here T0 value is being read, but it is being written. So if I execute like this T0, T2, T1 and store T0, 20 S2, you'll be storing a wrong T0 value. So if earlier T0 value was 6, and if this instruction is changing it to 8, and store instruction is supposed to store a value of 6. Okay, but here if I follow this order, T0 value would have been changed to 8, and you would be storing in this memory location a value of 8, which is wrong. Okay. So this kind of hazard is basically called as write after read hazard. So this to some extent can be resolved with the help of reservation stations. What you do? You store the T0 value as 6 in the reservation station. Okay, in the reservation station, and and by the time you are executing this add instruction, so you can take this value from the reservation station rather than taking it from the register file. Okay, so you update the register file, and whenever you want to execute this store instruction, if you want to execute this out of order, T0 value will be taken from the reservation station, and this can go ahead and modify the register file without any issue. Okay, so this is again another kind of hazard. Now we have talked about read after write, we have talked about write after read, then we have talked about write after write, and the one thing that is left is read after read. Do you think this will cause any issue? Read after read, should I consider it as an hazard or not necessary? It is not necessary because why? Why do you think this will not cause any hazard, not cause any problem? So there is one thing which is common among all of this. There is something that is getting changed. So there is something that is getting written. Okay, so when something is getting written, then you have to make sure it is getting written in a correct way. That's the reason we have to take care about these orders. But whereas in read after read, you only will be reading the registers, So you will not be writing anything. So in that case, it will not cause any hazard. Okay. So these are some of the important hazards that will occur in the dynamic multiple issue processors. Okay. So although I discussed in maybe 15-20 minutes, I don't know if you will believe me or not, the actual dynamic processor will basically involve some complex algorithms. So one algorithm is called as scoreboarding technique. The other one is called as Tomoslo's approach, which is a very complex algorithm which will take care of all of these. Okay, so that is basically a bit advanced. Maybe you can study it as part of your advanced computer architecture, or somebody is interested to take advanced VLSI architecture, you will be able to learn that particular algorithm there. Okay, I just gave you a brief idea about how your dynamic multiple issue processors work, but there is much more complexity involved. Okay, so how do you actually have a reservation station? Where is it connected? How do you issue the instructions? How do you make sure that there is no problem in execution of multiple instructions at the same time? Okay, so, and how do you keep track of which instruction is there in which stage? So all of that is maintained using different structures, data structures. So that's a bit complex and it's advanced stuff. Which this is just to give an idea about existence of dynamic multiple issue processors and problems that we might face in those dynamic multiple issues. Okay. Again, when you try to increase the ILP via dynamic multiple issue, there is always a problem with power consumption. So today's designs use multiple processors per chip, and these multiple processors are not deeply pipelined, or they are not aggressively using dynamic multiple issue. Okay, so they are simple processors, but the parallelism is achieved by scheduling or dividing the task into the different processors. Earlier, what they used to do, they used to have a single core which had a deep pipeline, okay, or it had a superscalar kind of architecture, superscalar, which is much more complex, which is much more efficient. But single core again had issues with the power efficiency. We have discussed this to some extent in the initial lectures. So that's why today's designs have multiple processors per chip, and those each processor is not deeply pipelined and not very complex in nature. So that way they are simple enough. The power consumption can be within a certain range, but the parallelism is still achieved in those with the help of multi-thread execution. So multiple threads are scheduled onto the different cores, and then execution can happen parallel. Okay. So simpler processes are not fast, but they deliver much better performance per watt because you can use multiple threads at a time. Multiple threads can be executed at the same time. So this is just giving you an idea about earlier, as I said, they used to increase the pipeline stages. Initially, they were talking about 5, then they went on to 10, then they designed the processor with 22 pipeline stages, 31 pipeline stages, and they kept on increasing the issue width also. Okay, so issue width here is 1, 2, and so on. But at some point, the power gap became too large to sustain this kind of a design. Then they went back to a design with less number of pipeline stages. Okay, so you have only 14 pipeline stages when you compare to 31 or 22. Okay, and you increase the issue width to maybe 4. Okay, and you have more cores per chip now. Okay, so if you see more cores per chip, the power consumption is somewhat less when you compare it with a single core version. So that way you are able to get a good power performance for the similar good power for a similar performance with respect to execution. Okay, so this is just to give an idea about that. So the main thing that you have to understand is today's processors are multi-core. Each processor will typically have reasonably less number of pipeline stages. So you don't have 31 or 22. Okay, in these Intel processors, you have 14 pipeline stages, and you have these processors to be multiple issue also. Okay, so whether it is static multiple issue or dynamic multiple issue is again it depends on the architecture, but you have issue size to be equal to 4, meaning 4 instructions can be fetched at a time. You have enough number of functional units to be able to execute those 4 instructions simultaneously, and all of that. Okay, so this and it also supports out of order execution, like the idea that we just discussed. Okay, so this is basically idea about improving your instruction level parallelism. Okay, so as part of this, we talked about static multiple issue processor and dynamic multiple issue processors. So dynamic multiple issue processors, again, there are, as I said, algorithms which you have to understand to really appreciate uh, what exactly it is. So, what is the advantage to understand that you have to go through these algorithms? One is called a scoreboarding algorithm, and the other one is Tomoslo's approach, which is more recent and which is used in most of your processors for out of order execution. Okay, so these are some of the algorithms which will be used in dynamically scheduled processors. I think with that, I'll basically I'm done with the discussion with respect to instruction level parallelism. Okay. So if you have any doubts with respect to the topic that I just discussed, please feel free to clarify that. Okay. Any doubts with these topics? Okay. So next class we'll be basically talking about I/O. Okay. So the IO related concepts, and I think that will be 2 classes, and there is one more class which will discuss about multi-core, just the basic idea of multi-core, not details. That will be winding up the course. So I let me now go to the other part which we wanted to show. I think it's been some time that we had the quiz. Okay, so we'll try to have that now. I think some people were waiting. I think I'm not sure whether they are available or not here. Today, I think I see even less attendance than usual. Okay, so are you ready? So this is a bit complex quiz. Complex meaning a bit concepts of cache and virtual memory will be there. So I hope you remember those concepts. It's been a long break for you. I hope some of you at least have kept in touch with the topics. Okay, so keep your mobiles ready then. Okay. You know the process, right? So you have to go to www.kahoot.it. You have to join using your ID number. So I see 15 students here. So I'll wait till most of you register. Okay, so should I wait? Three more students. Anybody facing some issue? Shall I start? Three more people yet to join. Four more people yet to join. Somebody joined just now. Okay, so shall I start? Anybody, if anybody is facing an issue, you let me know. I'll wait. Otherwise, I'll start. Anybody facing some issue? They want to join but not able to. Okay, so I think that's the strength. Now we'll start the quiz. Okay, we'll start. Okay. Okay. So anyway, we'll start. So miss rate is given with respect to instructions. You have to calculate it with respect to memory access. Okay, so three of them have answered correctly. Okay, so again, one miss every 25 instructions. So assuming 100 instructions, you have to check how many misses will be there. So that will be five. Five misses per 100 instructions. For 100 instructions, how many memory accesses will be there? How many memory accesses will be there for 100 instructions? There was one more information that was given, no? 25 load stores. So there will be 125 memory accesses, 100 for instructions and 25 for data. And when you're asked to calculate misses per memory access, this is 5 by 125. So 5 by 125 will be 0. Okay, so next question again is a bit complicated, meaning lengthy. Okay, whatever the terminology that you would like to use. Okay, so the next question. Okay, so let us see the toppers first. So we have 284, 554, and 450. So those are the three people who have answered it correctly. Okay, so let us move on to the next question. So this is on cache organization. Okay, again three people. So again, it's basically on cache organization. I think some of you have lost touch with the cache concepts, so that's why you are facing difficulty. You just have to calculate the number of sets. So there are 24 bytes. So from bytes, you have to calculate how many words. So from words, you will know how many blocks. From blocks, given it's a two-way associative, you will know how many sets. So based on the sets, you will be able to calculate how many index bits are required. Okay. 1024 bytes, and each block has two words, 32 bits, 64 bits. So 64 bits meaning how many bytes? 8 bytes. So 1024 by 8 will give you 128 blocks. But it's a two-way associative. Two blocks will make one set, so you'll get 64 sets. So 64 sets will require 6 bits for index. Okay, so that's how you solve the problem. Okay, so let me move on to the next. Before that, again, let's just see if there is any change. Okay, so new toppers have come. 476, 395, 528, 284, 554. That's the current status now. Later on, we'll get easy problems, but initially you'll get tough problems only. So let us, again, this is on cache size calculation. Again, a bit tricky. Remember, the address size is 16 bits, not 32 bits here in this problem. Okay, so 5 people have answered this correctly. Again, you just have to do some manipulations. So you have 256 blocks. In each of those blocks, how many bits are stored is what you are trying to find. So 64 bits data is anyway stored. 1 bit of valid is anyway stored. The only thing is you have to find out the tag bits. So 16 bits is your address. 2 bits you'll neglect. You're left with 14 bits. And then based on how many index bits you require, you'll be able to find the tag, and then you'll be able to calculate the answer. Okay. So let us see the standings now. Okay, again, few changes on top 5 has again changed. So 476, 528, 415, and 527 are the current toppers. Okay, so let us move on to the next question on page size coming to virtual memory. Okay, so 3 people have answered this correctly. You get 8 pages. There are 16 bits for physical address, 2 power 16 is basically the size in terms of bytes. You have 2K words. Word size is 32, I think. So 32 bits is how many? Uh, 4 bytes. So 4 into 2K is 8K bytes is one page. Sorry, 8K bytes is one page, and 2 power 16 bytes is the total size. So that will give you the number of pages. Okay. Okay, so let us move on to the table. Few changes. Again, new topics have come. Okay, now you have to be a little bit fast, so the questions will get very simple. The next three questions are very simple. It's not how. Uh, it's not just about the correct answer. It's about how fast you answer. So be ready to answer this very fast. Assume the bus size has 2 words only. Okay, so this was simple enough. So 8 people have answered correctly. Okay, so yeah, so new standings. So next few questions, it's more of a theoretical question. So you have to be very quick. The answer you will know for sure, but you have to be very quick in answering. Okay, so there are 2 questions left. Read the question carefully. Yeah, they're not quick enough. So TLB miss, cache hit, and page hit can occur. So for all of these three cases, page miss is there. When there is a page miss, there is no possibility of TLB hit. There is no possibility of cache hit. So that is why these three are eliminated. So only one choice is left. Okay, so let us see if there is any choice. Okay, so somebody has got the last three answers correctly. Okay, so it's basically saying that he's on fire or she's on fire. Okay, so let's just see the last question. So this is your last chance. So remember, the quickest answer will get 1,000 points. Okay, so remember that while answering the next question. Very simple. Okay, so 4 of you are. So swap space is something which will be there in secondary memory. If you remember the figure, that's where I showed. It's not there in cache, or it's not there in the processor, or it's not there in the primary memory. Okay, so that's basically the end of the quiz. So let us see the final toppers podium. So 527H, 476. And the winner is, yeah, who are these people? It's very hard to. Okay, so 395. Who is 395? AAP is 395. Okay, so complete. And then 476. 476 is Avinash. Okay. Avinash has been there in top 5 at least, I think, 2 out of 3 times already, right? And last 527. Who is 527? Keshav. Okay. So congratulations. Runners up, I think it's not very clear. I'll check and I'll update it. Yeah, I think that's all from my side today. So if you have any questions related to anything, you can let me know.
Sir,
Yeah.
I had a question regarding the assignment.
Yes.
So, in the assignment, for me, all three of the registers, X, Y, and Z, come to the same register. Like X, Y, and Z are all 4.
Okay.
So, for that, I implemented one type of
Hmm.
for just consecutive instructions. So that suffices for my instruction set, and I'm getting the right answer. But do I also have to implement the other sort of forwarding?
Other sort meaning?
The one from XWB to like the one where there it's like 2 instructions apart.
Do you think that will cause a problem here?
As in for my instruction set, it won't.
No, no, no. Generally, do you think you have not seen the processor? You have not seen the complete processor then? You have not gone through the complete modalities of the processor. It's not a 5-stage processor that you have to remember.
Oh, I
Okay. Anyway, I think with respect to you again, if that is working for you, it's fine, not an issue.
okay. Fine. Thank you.
But carefully go through the process. It's just a 4-stage processor.
Okay.
Whether the first instruction dependence on the third instruction will it cause any problem or not, that you have to look it up.
Okay.
Yeah. Somebody else had an issue with assignment. Yeah.
Excuse me, sir.
Yeah.
Sir, the design files which you told to submit through zip, those are the .v
Yeah.
files.
Dot v files.
Oh, okay. Thank you.
Yeah. Please.
Sir, can I show you my assignment document?
Yes. Yes.
Yeah. So, so this is my instructions. These are my instructions.
Okay.
So, for single cycle, I have to for move I have to read RY and just write into RX. For SLL, I have to read from RX and then write into RX.
Mm.
Again, the move is there. So for
Mm.
this, I read for both of them using the opcode. Like I show you.
No, I'll not be able to check the code. You tell me what is the
Okay,
issue with
okay.
the instructions. You had some issue
Yeah.
with the
So
instructions.
in the single cycle, I read both of them, and then I have done the execution part, and it's coming all right. But for
Okay.
forwarding, so this is one type of forward. For these two, it is one type of forwarding, and this is another type of forwarding. Because for the first two, I have to forward the value of R5, which I put into in my ALU for the first instruction. I'm just taking the ALU result as the second input. So like I'm not doing any calculation. So the result is just the input. So that I have to forward it here first to R5.
Correct. Correct.
And for this, I have to forward this R5 to,
Yeah, that we have discussed in the class already.
yeah, but sir, I'm facing an
You
issue.
have to give preference. You have to give preference. So if both occur, then you have to give it the latest value should be forwarded.
Uh,
The we have discussed this in the class. How
yeah,
to
yeah.
handle
So
it. What are the equations? What are
I
the equations that we have to
implemented
check
one
for?
thing. So the implementation I have done for forwarding is that I'm checking the EXWBRD, which is this field, and I'm checking that with ID EX RD, which is the this field and this field.
So you have to implement only one type forwarding here. Again, 4-stage pipeline. You see, this is a 4-stage pipeline.
Yeah.
Okay, so you will require only one type of forwarding. There is no dependency of first to third instruction here. The latest value always is there.
Yeah.
You have to check, double check it once again. There is no issue with the instructions or with the forwarding. There
Yeah,
is no difference.
the issue is not
There
with the
is,
instructions. The issue was with
and
how I
there
was.
is no there is no problem with the forwarding because the same thing we have already discussed in the class also. When you have 3 instructions, if there is any dependency. But I think there will not be a problem if there is a dependency between first and third because this is a 4-stage pipeline, not a 5-stage
The
pipeline.
problem, the only thing is that this R5 I have to read and write both in this thing only.
Yeah, it will not cause any problem. That's what I'm saying. Because RD anyway will be R5 only. You only check for RD, no?
Yeah.
So RD, whatever be the RS1, RS2 field, it will not matter. Only your RD field matters, and that anyway is R5.
Okay.
So you just have to manipulate your equations. So there is no, it's not that difficult. You just have to manipulate the equations.
Okay. Yeah. Okay. Thank you.
Anybody else has any issue with the assignment or anything else? Okay, so if not, then that's all from my side. Thank you.